With the gear train in place, all that's left is to create a coupling mechanism between the engine and the rest of the drivetrain. Create a new script and name it clutch. In between our engine and transmission, we need some sort of coupling mechanism in order to modulate engine speed independently from the rest of the drivetrain. This is where the clutch comes into play. The clutch is a friction disc that's meshed with the transmission and sits right beside the engine's flywheel. When the clutch is engaged, the friction disc rubs against the flywheel, causing it to roughly match the speed of the engine, allowing power to flow downstream from the engine to the rest of the drivetrain, and for drive load from the driven wheels to flow upstream towards the engine. When the clutch is disengaged by pressing in the pedal, the friction disc disconnects from the flywheel, allowing the engine and the rest of the drivetrain to spin independently. Because of the non-meshed coupling employed by the friction disc, there will always inherently be a difference in angular velocity, called slip, between the engine and the transmission. When the engine accelerates the wheels, the engine spins a little bit faster than the transmission. When the wheels accelerate the engine when coasting, for example, the transmission spins a bit faster than the engine. The amount of slip between the two sides is determined in part by the clutch's torque capacity, as well as its stiffness. We can sort of think of the clutch as a spring, where the amount of torque transferred is determined by the slip speed and the clutch stiffness. Using this concept for our real-time clutch simulation, what we need is a way to first record the difference in speed between the engine and the transmission, and then use it along with the clutch's stiffness to get the amount of torque transferred, making sure to clamp the output by the clutch's torque capacity. This way, when the clutch is engaged and a difference in angular velocity is observed, the clutch transfers torque to induce an angular acceleration and equalize the difference. Let's bring this concept to our simulation and implement the coupling mechanism. In our clutch script, we'll first get the clutch engagement by getting the complement of our clutch pedal input. And after checking if the vehicle is in gear, we'll get the slip between both sides of the clutch. We'll then multiply the slip with the clutch's stiffness to get the clutch's raw torque output, and then integrate it and multiply by a damping coefficient in order to simulate the springs found on a clutch disc, whose job is to dampen driveline vibrations when large changes in torque are made quickly when we're engaging the clutch, for example. Finally, we'll clamp the torque output by the clutch's torque capacity before sending it through the rest of the drivetrain. Save the script and attach it to the drivetrain empty, and configure the torque capacity, clutch stiffness, and clutch damping appropriately. And with our final drivetrain component in place, we're finally ready to connect everything together.